Hello and welcome to another one of my A-level videos for my Year 12 students. Hi guys, I hope you're all doing really well. I hope you're staying safe out there and enjoying your A-level physics. Okay, so today we're going to talk about centripetal acceleration. So the Year 12s would have just had a lesson from Miss Kennedy about circular motion basics. I'm going to recap a few of those just a little bit because otherwise it doesn't really make sense when we talk about centripetal acceleration without recapping some of those key points. Okay, so what we're trying to do today is we're going to learn how we can have a look at vector diagrams and use those to derive the equations for centripetal acceleration, and then how are we going to use those equations. The equations themselves are really simple. How we get to them takes a little bit of thought and a few leaps. As always, for the Year 12s, what I would like you to be doing is taking notes. So pause in video whenever you can, take some notes. Imagine you're actually in the classroom with me. There's not going to be an awful lot of questions, although there are a couple. I'd like you to pause, write down your answers, and then there is a question at the end, a calculation question, which can be done in two ways. Obviously, again, I'll let you know, pause the video, do the work, and then I go through the answer at the end. Okay. Okay, so to do this, we're going to have a quick recap of angular velocity. And what I want you to do is have a look at a clock or a watch and have a look at that for a minute. No, put down your phone, put down the digital watch. Yep, no, yep. You got a clock now, one with hands? Excellent, good. All right, what I want you to do is just watch that for a minute, and I want you to think about what's actually going on. And if you can't find one, here's a mock-up animation. So as you're watching these hands go around, I want you to think about what they're actually doing. They're going round in a circle, but really how far are they traveling? Where are they going? What's the displacement? So what did you notice about the second hand? Is the one that's going around the fastest, and I want you to focus on the second hand because it's one of the longer hands, and I asked you to watch it for a minute, so there's definitely some motion going around in a circle. Now, how fast were the hands going? What was the velocity of each hand? Remember that velocity is displacement divided by time. When you think about displacement, this is easy to demonstrate to students in a classroom because what I do at this point when I'm talking about displacement and velocity being vector quantities, what I will do is I will start on one side of my desk in my classroom and I will walk around the room and I will take an exaggerated weird path around my room and I will talk about the distance that I am traveling, each meter that I am walking, and I have an imaginary stopwatch in my hands and I'm recording the time, and I get to the other side of my desk and I stop my imaginary stop clock and I say, right, what was my average speed? And all the kids, this is normally a concept I teach to year 8 or year 9, all the kids will be able to say, well, it's the distance you traveled divided by the time you took. Great, brilliant, that is true. But then the tricky concept comes with the displacement. The displacement, how far have I actually moved, really? Yes, I walked all around my classroom doing a wiggly-waggly convoluted walk, but how far have I actually moved from start to finish? I've really only crossed from one side of my desk to the other. And so a straight line from my start point to my end point, that is my displacement. In terms of this clock then, what's the displacement of the second hand over a minute? Well, like any circular motion, the displacement, the total displacement, is zero. It hasn't gone anywhere. It's gone a full circle. It started and stopped at exactly the same place. Okay? So as we watch this hand go round, it starts at the 12 and it stops at the 12 and it keeps going round and round. So trying to find out the velocity of the hand is almost pointless because its average velocity over the minute is always going to be 0. So imagine instead the end of the hand is forming an arc, it's sweeping an arc. If you stuck a pencil on the end of the second hand and allowed it to draw a circle, as it went round, it would be drawing an ever bigger arc until it completes the circle. Now, as it's going round, it has an angle theta. So if you imagine, or just look at while it's going halfway round this animation, you look at the angle between it and the smaller hand. Okay, that's getting bigger and bigger until the smaller hand starts moving in weird animation. Okay, so here we go. Here's this in diagram form. In this case, we're starting at point A, and the second hand is going to sweep its way down a few seconds and reach point B. Okay. So the angle between point A and B is now the angular displacement. Okay, so our displacement is how far we have actually travelled. The angular displacement is the angle that has been swept by this arc. Okay, so from point A all the way down to point B, the angle that the hand has moved through, that is the angular displacement. That's a new terminology for displacement. How much has it moved around in the circle? And this is measured in radians. Okay? Radians were covered in your last lesson, but for anybody watching who doesn't know, a circle is divided into 2 pi radians. Okay? You can look that up, look up another YouTube video, or just look it up on Wikipedia or something. But for those of you doing A-level physics, that is something you need to know. You need to be able to convert from radians to degrees. Okay, so let's go back to our equation for velocity. It's displacement divided by time. Well, now we've got angular displacement. And so we can come up with this new terminology, angular velocity. So the angular velocity, how fast this hand is going around in the circle, is now measured by its displacement divided by the time taken to go through that displacement. So one complete circle, that angle is 2 pi radians. Okay? So going around half a circle, that's pi radians. Going around a whole circle is 2 pi radians. So we can see that the angular velocity of a complete circle is 2 pi, that's the angle to go around the complete circle, divided by capital T. And this capital T is the time it takes for one complete revolution. It's the time period of the circle. Okay, so going back to our original question, how fast are the hands moving? That we can only really talk about in terms of angular velocity. But let's say we've got something else moving in a circle. Let's think about a satellite orbiting the Earth. You have a force pulling it into a circle, and you can measure the velocity of the satellite. Now, it's moving around in a circle, so again, we're going to go velocity is displacement divided by time. Now, the displacement here is the arc length. It's the length actually travelled over that portion of the circle. Now, the arc length, therefore, is the angle multiplied by the radius of the circle itself. Okay? So we give this as S, so that's displacement, is equal to the arc length, which is the radius times the angle. Okay, so if you can imagine now, the satellite has swept through an arc with an imaginary line drawn towards the center of the Earth, then the angle that has swept through is the angle in radians multiplied by the distance from the satellite to the center of the Earth. That's the radius, and that gives a displacement. That's how far that satellite has actually travelled. Okay, so we can use our velocity as displacement divided by time. So that's r theta divided by time. And we've already said that theta divided by time, the angular displacement divided by the time taken, is the angular velocity. So our instantaneous velocity, the velocity of the object itself, is the angular velocity multiplied by the radius. Okay, so there we go. Now, we have to always understand that because we're moving around in a circle, velocity is a vector quantity which must have a magnitude and a direction. If either of those things change, we have a change in velocity. If we have a change in velocity, we have an acceleration. Something has changed the velocity, a force has been applied, and we have an acceleration. And so this velocity is constantly changing. It can be a constant speed. So if you have something moving around in a circle, it can be traveling at a constant speed because that doesn't involve direction. As soon as you talk about its velocity, it's now constantly changing velocity. It's constantly accelerating. Okay, let's consider the case of a runner who is on a perfectly circular track. He's going to start on the start line and he's going to finish at exactly the same place. So we can immediately calculate his average velocity. He has started and stopped at exactly the same place, so his displacement is 0. He hasn't really gone anywhere. And divided that by any time you like will always give you 0. So his total average velocity is always 0. Now imagine he's now run a quarter of the circle. We can now instantaneously measure his velocity. And the velocity is easy to measure on the quarter circles because the velocity is always at right angles to the center of the circle. And so it will just be horizontal or vertical velocity. Now, I want you to notice what's happening to the arrow of the velocity as we go around another kind of eighth of a circle. Off he goes. And we now have a new velocity vector. Now, I hope you can see that if you were the runner, as you're running around, you are constantly changing direction. You're always turning right. Now, if you can imagine that in plan view, you're always turning right as you go around the circle. You're always turning towards the center of the circle. And I hope that you can see that that velocity vector has moved from the perfect vertical system to moving and turning towards the center of the circle. And as it goes around, it's going to be constantly moving towards the center until it's horizontal, and when he's halfway around the circle. And again, it's going to be moving towards the center as he goes up and around. So he's constantly moving towards the center of the circle. And as we look at circular motion and centripetal force later on, that's really important. It's really important to understand that we're always turning towards the center of the circle as we're going around. Okay, but how we measure the velocity here? We're now at an angle, so it's a vector, and so we merely take the vertical and the horizontal components, and then we can calculate that velocity. Okay, so let's suppose we have a circle, and there is a line from the center of the circle, radius r, connecting to an object at point A. That object is now going to sweep through an arc around the circle to point C, and that is going to go through an angular displacement of theta. So now imagine that the object is still going around in the circle, and it's going to go through exactly the same angular displacement, and it's going to go to point B through exactly the same angular displacement, theta. Now we can break down the components of the velocity. Now let's move to a slightly scarier diagram But if we actually look at the velocity of the particle at each point, at point A, we can see that it's moving to the right of the vertical, and point B, it's now moving to the left of the vertical. So we can break down these into the horizontal and vertical components. A and B are equal distances above C, and so the theta is exactly the same. Because the vertical components are exactly the same, then we can cancel them out. The velocity is the same, and so there is no acceleration between these points. Acceleration is the change in velocity divided by the time it took. If there is no change in velocity, again, we have 0 divided by some time, which is meaningless. We have no acceleration. So in the vertical direction, at these points, there is no acceleration. Okay. But what about the horizontal? If you look at that diagram, you still have v sine theta on both of those. Theta is still the same, v is the same. But now, if you just look at the directions, they're completely different. So at A, the horizontal component is v sine theta. At B, the horizontal component is minus v sine theta because it's going in the opposite direction. Remember, these are vector quantities. So if it's going in the opposite direction, it must be negative. And so we have an acceleration where we have a change in velocity divided by time. The change in velocity, the final velocity is minus v sine theta. Minus v sine theta gives you 2v sine theta. Okay, it's 2 times v sine theta, all divided by t. Okay, so if we have 2v sine theta divided by t, that's the acceleration in the horizontal direction. We go back to our definition of angular velocity, and we see that the velocity is equal to r theta divided by t. We can rearrange that quite easily to get t equals r theta divided by v. Okay, so we've got the radius multiplied by the angle that we've swept through divided by v. Remember that this angle is to go from A to C, and it's the same angle as going from C to V. So from A to B, we have moved 2 theta. We have gone through that angle twice. That angular displacement has been gone through twice. So now we can write that. So from A to B, the time it's taken is r, the radius, times 2 theta, all divided by the velocity. So we can substitute this back into our acceleration equation. We've got v times 2v sine theta, all divided by r2 theta. And this is because we substituted t at the bottom of the acceleration equation. And so we've had to multiply by v and divide by r2 theta. Now, if you look at this, we can clearly get rid of the 2's. They will cancel out. And the v times v is v squared. So we can rewrite this. Acceleration is v squared sine theta divided by r theta. Now then, we can separate out those components, and we can say that v squared divided by r multiplied by sine theta divided by theta. That's the acceleration. Now, we use the magical property that sine theta divided by theta is always 1. Okay? Sine theta divided by theta is always 1. That's a mathematical property that is known. So now, if we put that back in, we've got the acceleration in the horizontal direction is v squared divided by r. So the velocity squared divided by the radius. If you can remember, the velocity is given as the radius times the angular velocity. So we can substitute that back in, and we now have r times the angular velocity all squared divided by r. And we can simplify that. We can get rid of the r at the bottom to give you acceleration equals r times the angular velocity squared. So A equals R omega squared. Okay, so we can use this now. This would have been shown to you in the previous PowerPoint from Miss Kennedy, but here is an example. Apologies if this isn't very clear. But we're looking at a geostationary satellite, and this is one that is in the fixed position above the Earth. As the Earth rotates, the angular velocity of the satellite is exactly the same as the angular velocity of the rotation of the Earth. So if you were to look up in the sky, the satellite would be in exactly the same position at all times. So, this was a worked example asking you how you could calculate the angular velocity. So it's going to complete a complete orbit, the same rate as the Earth revolves, so that takes 24 hours. So the angular velocity is 2 pi divided by the total time, which is 24 hours. So that's 2 pi divided by 24 hours times 60 minutes times 60 seconds. So we've now got 2 pi over 86,400, which gives you 7.27 times 10 to the minus 6 rads per second. Okay, times 10 to the minus 5, sorry. Now, how quickly does the satellite rotate through this certain angle? So now we're calculating the instantaneous velocity. The radius of the Earth is 6,400 kilometers, and the satellite is 35,600 kilometers above the Earth's surface. So now we do V equals R omega. We just calculated omega to be 7.27 times 10 to the minus 5 radians per second. And so we add the diameter, the radius of the Earth and the orbit of the satellite. 6,400 plus 35,600. That's in kilometers. Multiply it by the angular velocity, and that gives you an instantaneous velocity of 3,050 meters per second. Now then, over to you. This is where I want you to pause the video, answer this question. What is the centripetal acceleration of the satellite? Okay, did you pause the video? Have you worked it out yourself? No peeking? I'm trusting you. Excellent. Okay, good. All right, so what is our centripetal acceleration? We can do this in two ways, in fact. So we look at acceleration is equal to the velocity squared divided by r. Okay, we know both of these things. We know that the velocity squared is 3,050, square that, and divide it by the total radius of the satellite, 6,400 kilometers plus 35,600 kilometers. And that gives you an acceleration of 0.22 meters per second squared. I hope that matches up with what you have. But let's look at the other way. We also said that acceleration is radius multiplied by the angular velocity squared. So now we've calculated this too. So the radius is the same, 6,400 plus 35,600 kilometers multiplied by 7.27 times 10 to the minus 5 squared. And again, this works out to 0.22 meters per second squared. Okay, so both methods check out and come to the same thing. Now, I hope you can appreciate that we've discussed things going around in a circle, and we've said that the velocity is changing direction at all times. And because the velocity is changing direction at all times, that means that there is an acceleration. We have changed the velocity. At any point in a circle, we can break down the components of the velocity, and we will always find that the acceleration acts towards the center of the circle. If you're turning round in a circle, you're always turning right. You're always turning towards the center of the circle. Now this means that because you're accelerating towards the center of the circle all times, there must be a force changing that direction. And that is what Miss Kennedy is going to go through in the next few lessons. You will hear from me again in a fortnight, where I will pick up and we will talk about electric fields. If you found the talking PowerPoints useful, please do drop me a line, and I'm probably, if I have enough time, as I said before, complete the course. So talk about centripetal force, talk about motion in a circle, and the other parts as well. And then hopefully you can have like a complete set of these videos for your revision. Okay, the last thing for me to say then is that I hopefully will see you all soon. So I would like you please to stay safe, and I'll see you soon.